with that. So last week, we started talking about motors. Now we're going to continue a little bit on with motors, and then we're going to look at alternators to start with. Cool. So alternators. Cool. So when current flows in a conductor, magnetic field is created around that conductor. Depending on the direction of current, will dictate the direction of the magnetic field. Rotates around the conductor. So we use the right-hand grasp rule. So basically, if you were to grab the cable and the current was flowing in the direction of your thumb, your fingers represent the magnetic field. So if you place a compass within the area of this influence, the magnetic field, the needle will align itself with the direction of the flux lines. Wherever it is moved around the conductor, the needle will always point in a direction circling the conductor. This also demonstrates that magnetic flux always points from north to south. But yeah, so for DC, we can say this magnetic field around the cable is constant in the direction, but for AC, we need to remember this will change 50 times a second with the frequency. We still need to take into consideration when we run our cables along cable trays that the magnetic fields will have an effect on each other. Cool. So in a magnetic field, so on the flip side, the conductor is moved within a magnetic field and EMF is induced into it. If you measure the voltage at the tips of the conductor, the voltage will be present. If the circuit is closed, the current will flow. The conductor and the magnetic field must have relative motion between them. Either the conductor must move within the magnetic field, the field move around the conductor, or both. So the magnitude of the EMF is induced into the conductor depends on 4 factors. So you've got flux density of the magnetic field, so how strong the magnetic field is, the length of the conductor within the field, the relative velocity under the between the conductor and the magnetic field, so how fast it's spinning, and the angle of incidence between the conductor and the magnetic field. Cool. So the angle of incidence plays a big part in our studies of the generation of electrical energy. As a magnetized rotor rotates past the windings in a stator, the angle of the incidence constantly changes, meaning the magnitude of the EMF induced constantly changes with it. This forms the sinusoidal waveform we all know as AC, the AC sine wave. Cool. So one of the basic laws of electromagnetism states that opposite charges attract and like charges repel. So in terms of the magnetic fields, so when 2 north poles are brought together, the forces between them push against each other. This is because the forces are going in opposite directions to each other, and so they collide. 2 poles don't want to touch, again, because of the forces. The same for 2 south poles, so whether you try to stick 2 north poles or 2 south poles together, don't want to do it. The closer they're brought together, the greater the force of repulsion. It's because more forces are colliding and pushing against each other. So the opposite is true for unlike poles. So a north pole and a south pole will come together. That's because the forces are going in the same direction and they basically combine with each other. Forces they exert are opposite, and this will couple them together. This contrasts with like poles. The closer they are to each other, the stronger the force of attraction. This is because more forces are combining and increasing the attraction force. Cool. The interaction of magnetic fields is a key concept in the operation of electric motors moving forward. Cool. So then we look at the simple alternator. So a simple alternator used to generate an alternating EMF consists of 3 basic elements. So you got a turbine, it's moved by an external force moving over it, such as water flowing. This turbine spins and provides rotational mechanical energy. The turbine can be spun by several different energy sources. In hydro, you have falling water, and wind, we use the wind pushing on the blades connected to the turbine. And for geothermal, we use high pressure steam. Same is true for coal or liquid fuel-based power generation. Cool. Magnetic rotor that is connected to the turbine via a shaft. This rotor can either be a permanent magnet or is magnetized by an external current flow. It's more common for large alternators to have an external magnetizing circuit, as it's more cost effective than having a large permanent magnet. A set of stationary windings positioned nearby but not in contact with the rotor. These windings make up the stator, which we looked at. So the difference between a motor and an alternator we use to generate electricity. A motor, we use electricity to do work. So the windings are made up of varnished copper wire. The varnish is what electrically insulates each winding from the other, but does not block the magnetic field. So as the turbine spins the rotor within the alternator housing, the magnetic field produced by the rotor cuts across the stationary windings, causing an EMF to be induced into them. This is called electromagnetic induction. The EMF being generated is connected to an external circuit, which can be used to power other equipment. It is a conversion from mechanical energy into electrical energy with a small percentage loss of heat. So the magnetic field induces an EMF. It does not induce a current. The current is a product of the voltage and resistance. So whenever we talk about something being induced, it's a EMF, not so a voltage, not current. Current is just the result of us inducing the voltage and giving it a conduction path. Cool. As the rotating magnetic field cuts the stator, its angle of incidence constantly changes. And we've learned maximum or peak EMF is generated when the magnetic flux lines cut the conductor at 90 degrees. When the flux lines are parallel with the conductor, there's no angle of incidence. Therefore, there is no electromagnetic induction occurring. The angles in between still cause induction to occur, but at a value less than the peak value, but proportional to the sign of the angle at the incidence. This instantaneous value can be calculated using the formula EMF instantaneous equals the EMF peak times the sine wave. Cool. If each instantaneous value is calculated for all 360 degrees of rotation completed by the rotor, the measured waveform resembles the sinusoidal waveform that we've seen in prior studies. The magnitude of the waveform is determined by the peak value generated at 90 degrees of incidence. It's important to know regarding our studies on motors because electric motors operate on the same principles, only in reverse. An alternator converts external rotational mechanical energy into electrical, whereas a motor converts external electrical energy into rotational mechanical. Cool. So when the magnetic field is perpendicular to the winding or at 90 degrees, we get the highest induced voltage, so peak voltage. When the magnetic field is parallel to the winding or at 0 degrees or 180 degrees, if you want to look at it that way, we get no induced voltage. We use the sine function because when we do any angle under 180, we get a positive value, and everything over 180, we get a negative value. This represents the actual voltage value and whether it is positive or negative at its cycle in the sine wave, at its point of the sine wave cycle. Cool. So let's give it some practice. Cool. So an alternator is producing a peak voltage of 325 volts. Calculate the instantaneous voltage when the rotor is at 30 degrees. Oh, so yeah, we take 325 and multiply that by the sine of 30 degrees, and we get 162.5 volts. Cool. So what about 45 degrees? I'll take the time to remind you guys that your participation in the chat when I ask questions is generally how I do attendance. So if you don't say anything throughout the whole night class, I will assume you turned on the chat and then walked away from the computer. Cool. Yeah. Yeah. 229.81. Yeah. All answers to 2 decimal places. Cool. So 85 degrees. Cool. So yeah. 325 times sine of 85 is 323.76. What about 170 degrees? So 170 degrees, you get 56.44 volts. What about 200 degrees? Cool. Yep. 100 negative 111.16 volts. So 250 degrees. Yep, can do. So I'll just write it on the board, shall I? Cool. So you've got basically it is A MF INST for instantaneous equal to MF max. I haven't left myself nearly enough room there. Cool. So EMF instantaneous equals EMF max times sine of the angle or sine theta. This can also be written as V instantaneous is equal to V max times sine of the angle, sine theta. Does that make sense? Cool. So I'm just going to take it off just so you can see the next value. So yeah, the answer for that was negative 305.4 volts. So the next one, 310 degrees. What have I done? Okay, cool. Yep. So negative 248.96. Sorry, I was just trying to fix something that's going on with the chat there. Cool. So what about 355 degrees? Oh, good. Sebastian has access to the chat now. Cool. Yep. Yeah, at 355 degrees, we have negative 28.33 volts. Sweet. Cool. That's how we use that calculation to find instantaneous voltages when we know the max voltage output of an alternator. Cool. So single phase or two-pole alternator, it consists of a motor rotor that has been magnetized using an external DC circuit, the two stator poles with windings coiled around each one, creating a circuit. In a lot of AC alternators, electromagnet is used as a rotor due to the ability to create stronger magnetic flux than permanent magnets. A DC circuit is connected via a commutator to the rotor to ensure the polarity of the rotor EMF is kept constant. This can be fed from a battery or rectified AC supply. So when we say rectified, rectification is the process of changing AC to DC. This rectified AC supply can even be drawn off of the alternator once it is running. However, there must be something used to create the initial electromagnetic force in the rotor to begin the process. The current that flows in the rotor is called excitation current. This current produces the magnetic field. The stronger the magnetic flux, the greater the amount of electromagnetic induction that occurs, thus a higher EMF output. This means that by adjusting the amount of excitation current, we can also adjust the amount of EMF that is produced on the output of the alternator. Typical setup might include a battery for the initial creation of the magnetic field, which is then charged via the AC supply once the alternator is up to speed, like via a trickle charging circuit. Cool. And then we have three-phase alternators. So three-phase alternator works on the same principle as the single-phase one, only there are three sets of windings in the stator, each displaced 120 degrees from each other. These windings can be used to supply three individual loads at the same time, but this would require 6 conductors to do so. Alternatively, one end of each winding can all be joined together to form a common connection between the ends of all three windings. This is the return path for all currents and is the neutral. So therefore, you could say, so this method of connection is star, which we also looked at while we're studying transformers. We can also apply this knowledge to generators and motors. We'll look at how the different connection configurations such as star and delta affect electric motors later. But for now, we're just looking at the alternators. So as we can see, each winding is physically 120 degrees displaced around the stator of the alternator. This means the magnetic flux peaks in each winding at a different time and displaces each phase by 120 degrees electrically as well. And here is a diagram showing how the spinning affects the current. So as you see there, they're each peaking at different times as the north and south pole are perpendicular, so at right angles to that winding. But as soon as it's head on, the north or south pole to it, it goes to 0. Cool. So rotor construction. Cool. So the fact is the way in which the rotor of a generator or an alternator is built is based largely on whether it is going to be a high speed or low speed alternator. As we've studied, there is a place for each of these speeds in generation. It depends on the prime mover causing the rotor to move. So low speed, so typically alternators in hydroelectric dams or wind turbines, the prime mover moves relatively slowly due to how the medium moves over the blades of the turbine. And then high speed, typically alternators in gas or steam-driven turbine systems. These are typically under high pressure and can be used to spin the prime movers very fast in relation to the lower speed turbines underwater or in air. The speed at which the rotor will be traveling has a major impact on the physical size and type of construction of the rotor. Higher speed rotors tend to be smaller due to the centrifugal force that acts upon objects. The larger the rotor, the higher the force it experiences at high speeds. When we say larger, we are mainly talking about girth. The alternators and therefore rotors in hydro and wind tend to be very wide but shorter proportionally compared to those in steam-driven alternators. Cool. So you got different types of design and construction. So keeping what we've learned in mind, there are two common types of rotor design used for generators. So you got salient pole rotors and cylindrical rotors. So salient pole rotor is comprised of a hub with multiple salient poles that point outwards from the center. Each pole is made of thick laminations of silicon steel with heavy gauge copper wire wound around each one to form a powerful electromagnet. A DC excitation current is driven through these windings to project flux lines towards outwards from each pole. The axial length of the rotor and the accompanying stator is often quite short, with many windings wound around each pole of the rotor. This makes for easy cooling, as well as the way that the rotor poles move air around, as well as sometimes with the help of a fan at the end of the rotor. So they're a lot easier to cool, and they're better, well, they're usually wider and shorter. Cool, and then you've got cylindrical. So a cylindrical rotor is built very differently. It is built for high speed efficiency and aerodynamics. So salient pole is more for your hydro and your wind, and the cylindrical is more your gas turbine. Cylindrical rotor is built, so they are longer in axial length, but often much smaller in diameter. They do not have a pole jutting out as salient poles do. They are instead made up of a number of slots in which fewer but larger windings are built into. The windings look more like solid bars and are laminated to insulate them from each other. The diagram here shows a cross-section of a basic 4-pole cylindrical rotor. The windings work their way through the slots. So you can see the slots there. So it's got 2 north poles and 2 south poles. So they work their way through the slots around each pole and wrap around the ends to form a loop. They do not protrude out of the slots, which gives the rotor its cylindrical look and name. Typical cylindrical rotor may only be 2 or 4 pole due to the speeds they can attain. They're also much more easily balanced and offer less running noise as the surface is much smoother. One of the greater advantages of the cylindrical rotor is its ability to provide a more even and stable AC waveform due to the flux being distributed more evenly around the rotor itself. This type of rotor is typically fixed to a turbine being moved by combustible gases or high pressure steam. So your nuclear or your coal or steam, like LPG and oil and gas powered turbines. Cool. Speed and frequency. So seen in earlier chapters, each time the rotor makes a complete rotation within the stator, one cycle has been completed and we can see a complete sine waveform. That is one position peak and one negative before returning to 0. The time it takes to complete one cycle is called the period, measured in seconds. And conversely, the amount of cycles per second is called the frequency, measured in hertz. So looking at the animation here, we can see that a rotor with one pair of poles produces one cycle as it moves past the pair of stator poles. We can use a formula to derive the frequency of the supply alternator if we know the rate at which it is moving. So the formula is F equals NP divided by 60, where F is frequency measured in hertz, N is the speed of rotation measured in revolutions per minute, and P is the number of pairs of poles. So if we knew the frequency we wanted to attain, we could therefore work out the speed and number of poles we wanted to spin at. So we know we need a frequency of, we know what frequency we want to attain. We can then rearrange the formula to figure out how fast we need to spin the alternator or how many pairs of poles we need. As we add poles, the formula showed us that the frequency is directly proportional to both the speed of the rotor and the number of poles present in the rotor. If we increase the number of poles in the rotor, we're essentially increasing the amount of times the magnetic flux of the rotor will cut the stator, windings per revolution. This way, we can increase the frequency by adding more poles in rather than relying on rotor speed. On the flip side, in order to provide a set frequency value, we can substitute speed for poles. Our generation network must supply 50 hertz, no matter the equipment that is generating it. We operate a combination of high and low speed rotor systems in New Zealand, so thus we must utilize various methods of maintaining a consistent frequency. Cool. So three-phase multi-pole alternator. So a three-phase alternator works in exactly the same principle as a single-phase one, only there are three sets of stator windings, one for each phase. In the case of a three-phase four-pole alternator, each phase must have its own set of four poles, and each of these poles would be wound 120 degrees offset from the next phase winding. And even larger alternators, the sequence continues. More poles means a higher frequency at the same speed, or conversely, a lower frequency at lower speeds if desired. The diagram below shows three-phase alternators. The left is four-pole, the right is 14-pole. So we need three sets of stator windings, one for each phase. You have a red, a white, and a blue. In the case of the three-phase four-pole alternator, each have its own set of four poles, and each of these poles are 120 degrees offset from the next phase winding. So even though they're more poles, they're still 120 degrees removed from the next nearest one. Then even larger alternators, the sequence continues. So more poles at low speed to generate the same frequency with less poles at higher speeds. So you see the one on the left there, that would be generally for your steam or gas-powered generation, because it will spin a lot faster and produce the same frequency as the one on the right, which is for a low speed, producing the same frequency. Oh, cool. So we had a look at alternators. Now we're going to talk about the universal motor. So just going off the name, why do you think it's called a universal motor? Yeah, basically hit the nail on the head. The reason we call them universal is because of that reason. We can use them on AC or DC. Cool. So while other motors we will learn about are called induction motors, so those are the main type of motors we'll learn about. The universal motor does not use the principle of electromagnetic induction to operate. It operates on the interaction of magnetic fields created by current flowing within a conductor. A universal motor will operate both on AC and DC. This is due to the operation principle of the motor interacting magnetic fields. An induction motor will not operate on DC. Cool. So magnetic flux lines are always form closed loop, either around a conductor or from north to south. They also never break and never cross, only affect and oppose one another as they form their circuit. So two conductors that lie together so that the current in each other is traveling in the same direction will form an overall magnetic field that couples together. Their flux lines move fluidly with each other to form one larger loop. Two conductors that oppose each other's current direction, however, will create flux lines that oppose each other in direction and therefore push against one another. If enough current were to flow and the magnetic fields become so dense with flux, they would physically push each other apart. And there used to be a video that we had that showed it. Three-phase cable sitting on a cable tray. All of a sudden, the magnetic fields kick up and then just they blow each other apart. The only thing that holds them down are the steel cable ties. Cool. And so remember Fleming's left-hand rule. You can see it here. So the left-hand rule determines the direction of movement if flux and current flow are already present. That is, if we apply current to a conductor in a magnetic field, we can figure out which way it will move. So always remember left and right-hand rules. Yeah. So your left hand is for your motors, your right hand is for your generators, okay? You generate and you use what's left, okay? Using one left hand, we extend our thumb, forefinger, and middle finger, so they point in 3 different directions. Thumb straight up, forefinger straight ahead, middle finger pointing away from your palm. Each of these represent an aspect of Fleming's work. The thumb indicates the direction of movement. Something will move in when subject to the other 2 aspects. The forefinger represents the direction of the magnetic flux lines, and the middle finger indicates the direction of current flow at any one instant. So no matter whether we're talking about the left or right hand rule, they're both, all fingers mean the same thing. It's just the right one is for generators, the left one is for motors. Cool. We can see how Fleming's left-hand rule comes into play when a conductor carrying current is placed within an external magnetic field. The flux lines around the conductor interact with the flux lines of the external magnetic field, causing the conductor to be moved out of the external magnetic field. Using the hand rule and aligning our forefinger and middle finger with the flux and current respectively, we can see that the conductor moves in the direction our thumb is pointing. So the way we know which way the current is moving is because we can see an X. Yeah, I think they've drawn that wrong. Cool. We can also pretty much judge which direction the conductor will move if we look closely at the 2 sets of flux lines. The external flux lines naturally want to flow with the conductor flux lines. So all bunched together on one side, they cannot cross each other though, so they stretch. Wanting to return to equilibrium, they push the conductor out of the field so the flux lines can become straight again. This process is the first step in understanding how a universal motor works. Next, we will look at the wiring configuration so that this sort of magnetic interaction can occur to create movement. So, yeah, the way we know it's moving, the current is moving out of the page is because, no, it's moving into the page is because it's an X. So if you think about an arrow, if you fire an arrow, you can see the feathers at the back and sometimes they make a cross section. Whereas if the arrow is flying towards you, you just see the pointy end. So if it's a dot, it's coming towards you. If it's a cross, it's going away from you. Cool. So how it works. So this is the diagram for a universal motor. So we can see it's got 2 stator windings and are connected in series with the rotor in the middle. The rotor is comprised of another set of windings that create a full circuit when connected to the brushes on each side. A simplified universal motor might have one winding wound around the rotor armature several times, whereas a common universal motor will have several, each connected end-to-end to segments on the commutator, so that each winding is connected at a different time during the motor's operation. As current flows through the stator windings, they create their own magnetic field that cuts the windings of the rotor. At the same time, current flows through the rotor windings. These then generate their own magnetic flux that interact with the flux that the stator windings are emitting. The nature in these magnetic fields interact. The nature in which these magnetic fields interact causes rotation of the rotor. Cool. So, hopefully this works. Here we go. Cool. So let's have a look at one. So this here is the universal motor we use in the workshop for you guys to wire up and have a go with. So you can see it's mounted on a base plate. And here you've got the field windings. You've got a brush here. And on the other side, you've got another brush and another winding. There we go, refocus the motor. So here you've got the motor itself. So here you can kind of see in the middle here, you've got the brush connection to the rotor. You can see I can freely spin it. Let's get you a better look. So yeah, you can see the brushes there spinning on the rotor. Let's light this up a bit. I don't actually know how much that light helped. Cool. So yeah, you can see, and then if you look, it's going to get a bit awkward. Down this way, you can see the rotor windings in there spinning as I move it. And then you've got the outer windings that don't move. Okay, so this is a basic little mini universal motor, kind that we use here in the workshop for you guys to play around with. I would hook it up, but I'm inside of the virtual classroom rather than out on the shop floor. Okay, so let's turn that off. Give it a sec while it goes back to now it won't turn off. There we go. Cool. So this diagram shows a universal motor with its stator windings and a rotor consisting of a winding wound on the armature. The rotor winding is represented by the cross and dot circles, symbolizing the windings wrapping around the armature from a dot into a cross. This effectively means the current is flowing towards us on the right-hand side of the armature as we are viewing it, and away from us on the left. The way in which the windings are wound on the armature will affect the direction of rotation that the rotor will move when current flows in the circuit. As we can see, current flowing in the stator windings create a magnetic field with flux lines crossing the rotor from north to south. We'll call this the stator flux. We'll call the flux that surrounds each of the rotor windings the rotor flux. And we use Fleming's left-hand rule. We can determine which way it is traveling around each turn. Given the direction of the rotor flux around each turn, we can see that this flux will interact with the stator flux in such a way that causes the rotor to travel clockwise. Each time the armature rotates, the connections between the supply and the rotor windings is reset, meaning that the polarity of the current within the rotor windings is the same all the time. And just because it'll help you when you guys get to block course, if you ever need to reverse a universal motor, basically just swap the field windings around. So basically, you just literally take the phase and the neutral and you swap them around. That's how you reverse a universal motor. It's the same as if you took the positive and negative and swapped them around. Cool. Alternating current supply. So when connected to AC, the same principles applied, only the current direction changes every half cycle. This much we know already. However, when we change the direction of current, we also change the magnetic polarity of the stator. We can apply another rule to understand this better, the right-hand grasp rule, rule number 2. This rule tells that if our finger follows the current flow around a solenoid coil, then our thumb will point in the direction of the magnetic flux lines. Looking at the diagram, the first half of the cycle has current flowing out of the right-hand side of the supply and towards the right-hand stator coil. The current travels downwards in front of the coil first, and then ducts underneath it and back and up on the back side. If our fingers follow the coil, then our hand is extended in front of us, palm side up, and our thumb is pointing to the right. The current then flows in the rotor at the same time and generates a magnetic field in such a way that causes the rotor to spin in one direction or another. In this case, it is clockwise. Now, when the polarity of the supply changes in the second half cycle, two things change: the direction of current flow and the direction of the magnetic flux across the stator. So even though the magnetic field is changing, so is the magnetic field, so is the current flow inside the rotor, which means that it actually continues to go the same direction. Cool. So characteristics: it has a high power to mass ratio. So this means that a universal motor is capable of achieving a great deal of output power for its size. A small motor is able to apply a lot of force to a load in comparison with other motors of the same size. This also means that the universal motor can achieve very high speeds with no load present. So much speed, in fact, that the motor can destroy itself due to the high levels of centrifugal force being applied outwards from the rotor as it spins. Thus, it is crucial that all universal motors are run with a load present. When a load is present, speed is restricted and the destructive centrifugal force are kept in check, which is why when you run these universal motors that we have here at Block Course, you do not run them for very long because they will blow up if you keep running them. We don't run them loaded simply because we haven't yet been able to find a way to load them safely. We have been able to load them up, but it's been dangerous, and so we try not to do it. So when it talks about high power to mass ratio, so you'll find universal motors inside of all kinds of things. So last time, the most recent one I found, I opened up a friend's washing machine, and the motor spinning the drum of the washing machine, it's an 8-kilo washing machine, was a universal motor. So they can do a lot of work for their size, and it was not a lot bigger than the one that I just showed you. I'd be able to fit the motor on my palm. I wouldn't be able to hold it, but it would fit on my palm. And also all of your guys' battery drills and impact drivers are universal motors. So they can put out a lot of torque. Impact wrenches are universal motors. Cool. It's why we can get low speed, high torque and high speed, low torque out of them. Another characteristic of the universal motor is they have very high torque at low speeds, and conversely, they have very little torque when moving at high speeds. If we use a drill to put a hole through a piece of timber with a 25 mil auger bit, you would typically pull the trigger slightly to allow the drill to power its way through the wood. If you were to pull the trigger right the way back, it would stall. This is the speed torque characteristics in action. We can represent the relationship between speed and torque on a graph here. We can see the rated speed and torque values indicated on each axis. In reality, these can be expected, but at the detriment of the motor. These can be exceeded, but at the detriment of the motor. As mentioned before, if the motor is left to spin too fast, centrifugal forces will destroy it. The same applies to torque. If too much load is applied at low speed, the motor will burn out. Yeah, that's why when we drill with big beefy drill bits or auger bits, we always put it onto low speed setting, or we use a special auger drill that has only a low speed. I worked with an old crazy Scotsman who had a corded drill that did not have a, basically the low speed setting did not work, but he still insisted on using a 25 mil auger drill bit to drill through a whole bunch of laminated timber. LVLs, laminated veneer lumber, the big beefy structural timbers. And he was drilling through it on high speed, and we were so shocked that he did not break his wrist. Crazy, Ian. Cool. So the construction. So you got the stator. The stator of a universal motor is built very similarly to other types of motors. We know there is a winding that current flows through, but there must be something holding that winding in place. A frame made of laminated iron slots wraps around the winding, forming what is called the field poles. They are called field poles as they make up the magnetic poles that are where the magnetic flux enters and exits and is most concentrated at these points. As mentioned, these poles are made of thin laminated slots of iron or silicon steel. This is to limit the losses within the motor as current is induced into the field poles. Being thin slots, they are of a higher resistance than single solid block, therefore reducing current flow. Each slot is insulated from the next to it with a thin layer of varnish. One winding is then wrapped around a field pole, with one end connected to a supply terminal and the other to a carbon brush which transfers energy into the rotor. The other winding is connected in just the same way, symmetrically to the other. Cool, and here you have the rotor, you have your brush, and you have your winding. So the rotor of a universal motor is a moving part that has a winding in it. This winding is connected to the stator circuits via carbon brushes and a commutator. The carbon brushes are soft enough to maintain a constant connection with the moving commutator and not cause harsh scratching, but hard enough to last a significant time. These brushes are held onto the commutator with springs and conduct well enough to supply the current required. The rotor is comprised of a frame called an armature and a winding that is wound onto the armature and connected to the commutator. The design and construction of the rotor is dependent on the requirements of the motor. The rotor is held in place by a bearing at each end, which is mounted securely to the motor frame. There is a small air gap between the rotor and stator poles, and the bearings hold the rotor so that it is perfectly centered, or there would be an uneven magnetic field effect. Cool. So other parts. The universal motors are also comprised of other parts, such as a housing or frame. Motors that are used in portable appliances and tools must be insulated from the user. These housings are often made of metal that is connected to earth or plastic if it is double insulated appliance. You have a fan. The fan is mounted on the shaft of the rotor, so when the rotor spins, it also spins the fan. This makes the motor self-cooling. So you have a look at the back of your drill or impact driver, they normally have a fan mounted on the back. A speed governor. So universal motors can achieve very high speeds. So in some cases, a speed limiter of some description is fitted. This could be a centrifugal switch, a voltage controller, or even a load such as a gearbox to ensure the motor doesn't spin itself into destruction, which is why your drill has gears. Short bearings. These hold the motor shaft in place and allows for smooth rotation. A gearbox, this supplies a load to the motor so that it does not exceed its maximum speed and destroy itself. It can also increase torque output. And you've got your brush holder and springs. These hold the carbon brushes and allow connection from the external circuit. The spring applies force behind the brush to hold it in contact with the commutator at all times because carbon brushes will eventually wear out over time. Cool. So you've got different types of speed control for universal motor. So you've got your tapped field windings. So another name for the stator field is the field winding. Stator winding is the field winding. The length of winding directly affects the speed of the motor due to the magnetic field influence. So as you see there, the speed controller is just a tap switch. So you've got your three speed settings, your high, your medium, and your low. So basically high speed makes a shorter winding, medium speed makes it half as long as low speed, which makes it the longest. Yeah, pretty straightforward. You're basically changing the length of the rotor, which adjusts, which lowers the resistance, which increases current flow. Cool. And then you've got variable resistor connected in series. So basically, you're using the resistor to reduce the current flow. So yeah. The variable resistor connected either in series or parallel with the stator winding. It'll affect the speed of the motor. The resistor must be graded to operate continuously in the circuit. The series connected variable resistor reduces the amount of current flowing in both the rotor and the stator. This will reduce the magnetic field strength in both components and result in the slower rotation. The parallel connection, parallel connected variable resistor acts as a bypass to the field winding. A constant current will flow through the stator. However, current will also flow through the variable resistor, meaning that the rotor receives a different value of current than the stator. This varies the effect of the rotor's magnetic field and the interaction between the rotor and stator. The parallel connected method gives greater starting torque and smoother torque transition and control as the variable resistor adjusts in value. And then you have a variable centrifugal governor. So when we talk about centrifugal switch or governor, it's basically as the motor speeds up, it either clicks in and out. So if a motor has a centrifugal switch, that switch is constantly connected until the motor spins up to speed, in which it opens, usually used to connect some form of capacitor in an induction motor. Cool. So speed control, it uses a mechanical switch that opens circuit once the motor's reached a certain speed. It is set to contacts mounted on the shaft of the motor that changes state depending on the amount of centrifugal force applied to it. The switch is in a normally closed position until the motor turns on. Once the motor is up to speed, it will open. The motor then slows down until the contacts are closed again and the cycle continues. Speeds can be made variable by introducing a set screw that tightens against the contact and holds it closed for a fraction longer. This method of speed control is considered older and is used in applications such as food mixers, cameras, and projectors, although becoming slowly more and more obsolete. And then we have electronic speed control. So universal motors can also have their speed controlled through electronic means. Often a PCB or printed circuit board accompanies the motor and can have a variety of electronic components, including semiconductor devices being utilized. And because the PCBs are becoming and components are becoming smaller and smaller, they can now be fitted inside of our battery drills and impact drivers. But it is a pain when they blow, the PCBs blow up because you have to send them away to get repaired. Normally they just swap out the circuit board. I've had it happen to my drill twice in the past 2 years. Specialized electronics can accomplish half wave or full wave control to vary the energy being delivered to the motor. It can be done in a number of different ways using different electronic components. At this stage, it's only a requirement that you're aware of this. Look into how it is accomplished more in depth when you study electronics. Cool. So, direction of a universal motor. So changing the direction of a universal motor is not as simple as purely swapping around the phase and neutral connections in the terminal box. And this accomplishes nothing as the current still flows through the field windings and the rotor windings in the same direction at the same time. In order to reverse the direction of a universal motor, the supply polarity must be swapped on either the field windings or the rotor winding, but not both. This is done most easily in the field winding, where a tapped winding and two-position switch is used. This method of reversal works for both AC and DC supplies. Another method is using a bridge rectifier circuit with the field winding. Bridge rectifier only allows the current to flow in one direction, so if the supply is of a particular polarity, the motor will travel in one direction, and if the supply is reversed, so is the motor. This method, however, only works with a DC supply. Basically, what that means is you take a field winding and you swap the phase and neutral connection. Before you get to the brush for the rotor. So instead of going from You guys will see when you have to do it in a block course. Cool. Applications of universal motors. Universal motors tend to range up to about a kilowatt in ratings due to their construction comprising of brushes and a commutator. They are not often used in equipment designed for continuous use due to wear on the brushes. They also release a large amount of electromagnetic interference due to the sparking that can occur between the brushes and commutator. Despite being small and powerful, they are not the most efficient motor. Large motors can be around 70% efficient, with smaller ones only managing approximately 30% efficiency. In saying this, universal motors have their place in industry. Their high speed and high starting torque characteristics make them ideal in a number of applications. So these include portable drills, saws, and other hand tools, hair dryers, blowers, and vacuum cleaners. Kitchen appliances such as blenders and food processors.